Hey everybody. Today we're talking about implicit differentiation. Let's start with an example that might be familiar. X squared plus y squared equals 1, which represents the unit circle. Now, this is not a function. It doesn't pass the vertical line test. But we can still draw tangent lines to the graph and potentially talk about their slopes. So it seems like we ought to be able to compute dy dx, the derivative, even though this is not a function y of x. Implicit differentiation is a technique that lets us do that. The big idea is to view y as a function of x, even though it technically isn't, and then to differentiate the entire equation with respect to x. Since we're viewing y as a function of x, let's write y of x to stress that. Now, when we look at that middle term, we see that we have a composition. We have an outside function, the square, and an inside function, y of x. So when we differentiate this, we're going to need to use a chain rule. We get 2x plus 2y dy dx equals 0. In that middle term, the 2y is the derivative of the outside function, the square, and the dy dx is the derivative of the inside function, y of x. Notice here we're not explicitly calculating dy dx in that step, we're just writing down the notation for the derivative of y with respect to x. The idea is we'll solve for dy dx next. We're going to subtract 2x from both sides, then divide by 2y and simplify to actually get a formula for our derivative. dy dx is negative x over y. Now, if we have any ordered pair x comma y that satisfies this equation, so a point that lies on the graph, we can just plug in to get the slope of the line tangent to the graph at that point. For instance, let's take the point negative 1/2 comma root 3 over 2, which satisfies this equation, and plug it into our formula for the derivative. We get about 0.58, root 3 over 3. If we sketch the circle and plot the point negative 1/2 root 3 over 2, and draw the line tangent to the graph at that point, we can see that its slope is about 0.58. Let's do a slightly harder example. Find dy dx if y to the 5th plus 3x squared y squared plus 5x to the 4th equals 12. So our process here is going to be exactly the same. View y as a function of x, differentiate the entire equation with respect to x, applying the chain rule whenever we get to a term with y's in it, and then solve for dy dx to get a formula for the derivative. Here, however, the computation is going to be a little bit harder. In particular, looking at that middle term, we see that we have a product, 3x squared times y squared. And the second factor in that product is going to be a composition, y of x squared. So I'm going to need a chain rule on that one too. So let's differentiate. We go through term by term. The y to the 5th differentiates to 5y to the 4th dy dx using the chain rule, plus, okay, now we're using the product rule. We differentiate the first to get 6x, multiply by the second, keeping y squared the same, plus keep the first term the same, 3x squared, times the derivative of the second. So differentiating y squared, we get 2y times dy dx, and applying the chain rule. The other two terms differentiate to 20x cubed and 0 respectively. Now we want to solve this for dy dx. So I'm going to move everything without a dy dx off to the other side, keeping everything with a dy dx alone there on the left. Next, I factor out dy dx from the left-hand side. So the left-hand side is dy dx times 5y to the 4th plus 6x squared y. And then I divide by that quantity in parentheses to get a formula for dy dx. Overall, negative 6xy squared minus 20x cubed over 5y to the 4th plus 6x squared y. One final example. Compute dy dx if 3x over x squared plus y is y cubed minus 1. Again, we're going to view y as a function of x and differentiate the entire equation with respect to x. This time, the left-hand side requires a quotient rule. We take the bottom, multiply it by the derivative of the top, then subtract the top times the derivative of the bottom. Here I've written y prime instead of dy dx just to keep things a little bit neater. Then we divide by the square of the denominator. On the right-hand side, we're going to need a chain rule. Y is a function of x, so the derivative of y cubed is 3y times y prime. Now we have to solve for y prime. So I'm going to multiply both sides by x squared plus y squared to get rid of the denominator. Move everything with a y prime to the right, leaving everything without a y prime on the left. Again, factor out a y prime on the right, and then divide by the thing y prime is being multiplied by. Now I've isolated the derivative y prime. Overall, in this case, I get that the derivative y prime is 3x squared plus 3y minus 6x squared over 3x plus 3y squared times x squared plus y quantity squared. Again, we can plug in values that satisfy this equation to get the slopes of lines tangent to this graph. So, for example, 0, 1 satisfies this equation. That's going to be a point on the graph. And we can compute the slope of the line tangent to the graph at that point just by plugging in. When I take x equals 0, y equals 1, I get that dy dx is 1. Let's graph this. Here's the graph of the relation 3x over x squared plus y equals y cubed minus 1. At the point 0, 1, we can see that the tangent line has a slope of 1.